Okay, welcome back to another video on derivatives. This time we're talking about hyperbolic trigonometric functions. So what the heck are those? Well, if you actually take a look on your calculator, you'll probably see a button called sine H or hyperbolic sine. My math teacher in university called it shine, which is kind of cool. This function, although it does have a sign there, it's not actually a trig function, although you can see that when you take derivatives, it has similar properties. There's also hyperbolic cosine, or as my math professor back in the day affectionately called it, cosh. So anyway, these are the two functions that we're going to talk about. There are other ones as well, hyperbolic tangent and hyperbolic reciprocal trigonometric functions. But we'll focus on these two in this video, although I will include the hyperbolic tangent in the final example and even do a little proof at the end. So what's going to happen now? Well, we got to talk about these derivatives. So here we have hyperbolic sine. Much like the derivative of regular sine, it's going to be hyperbolic cosine. So look at how nice that is. Now, what do you think the derivative of hyperbolic cosine will be? When it's trigonometric, it's just negative sine, but in this case, it's actually going to be hyperbolic sine without the negative sign. So they just bounce back and forth. All right, let's take a look at the derivative of this first example. We have hyperbolic sine of 5x plus 3. So when we take the derivative, we end up with the derivative of hyperbolic sine, which is hyperbolic cosine. That's really fun to say. And then you would do a chain rule here by putting a 5. Of course, you could just write this as 5 times the hyperbolic cosine of 5x plus 3. And that's your first example. So take a look at that. Hopefully nothing too dangerous. We'll take a look at 3 more examples, and then we'll finish off with the proof at the end. In this next example, we have a couple of layers of chain rule, which the outermost layer involves the hyperbolic cosine. So the derivative of the hyperbolic cosine is just the hyperbolic sine. And hopefully that doesn't scare you too much. We now have to work on the inner layer by taking the derivative of the logarithm, the natural logarithm. We covered these derivatives in an earlier video. In this case, we know the derivative of a logarithm, or a natural logarithm specifically, is writing the reciprocal here. So we'll have 7x squared plus 1, followed by the chain rule, or the derivative of that, which is 14x. I just like to put the 14x on the top as such. And that is the derivative. So moving on now, we can take a look at another example. Hopefully, sine within sine, hyperbolic sine within hyperbolic sine. Well, this is looking a little bit dangerous, so hopefully we can sort this one out. This is a matter of bookkeeping. It's actually much shorter than the previous example. This would be the hyperbolic cosine of the hyperbolic sine of x multiplied by the derivative by the chain rule of whatever's inside this bracket. So what's the derivative of hyperbolic sine? Well, that's just hyperbolic cosine. All right, I'm just going to put a little dot here, and that'll be cosh of x. Yeah, I said cosh, just like my university professor. Anyway, now that I'm a professor, I guess I can make up my own funny names and funny sounds, as long as they're logical, though. Let's take a look at the one last example. Hopefully nothing too scary. It's the derivative of the hyperbolic tangent of x. Now, in this case, you might want to guess what that derivative is, but when we actually do the derivative, I'll do it the long way, but I will only use hyperbolic sine and cosine. We will need this identity to do this. This is a Pythagorean type identity that can be used to complete this question. Now, you could also hypothesize, well, the derivative of tan is secant squared. So what do you suspect the derivative of hyperbolic tan would be? To no shock, it actually is going to be the hyperbolic secant squared. So we're going to actually derive this right now by using just hyperbolic sine and cosine as a reference. So here we go. Let's start off by writing the original function as the ratio of the hyperbolic sine over the hyperbolic cosine. I will apply the quotient rule here. So actually, this is not a derivative yet. Let's get it organized there. So what is that derivative? Well, how's your quotient rule? in your memory. Hopefully you haven't forgotten it. It was several videos ago. I like to put the quotient rule several times in these videos in case you lose track or haven't seen it for a while. Let's move those over for a bit. Okay. So we'll do the derivative of the top, which is hyperbolic cosine. Then just copy the bottom, which is hyperbolic cosine. Then we'll copy the numerator and take the derivative of the denominator, which is hyperbolic sine. All right. And then over the denominator squared, which is the hyperbolic cosine of x all squared. What you notice in the numerator is precisely the identity that I've presented up here. I guess I'm going over this territory. Maybe I can just squeeze it in a little bit better. There we go. Okay. Well, anyway, that numerator is just going to be hyperbolic cosine squared of x minus hyperbolic sine squared of x. This is a lot of fun to say, trust me. And that numerator equals 1. So this is equal to 1 over. Oh, I got tired of typing it, so I'm just going to copy and paste this. There we go. And there you have it. It's the hyperbolic secant of x squared. Okay, I think I said that correctly. I love doing these videos in one take because you get to see me suffer and hopefully not get too messed up with what I say. There you go. Let's try to actually do a little bit extra here. I want to derive for you the relationship that I mentioned earlier, which is this identity here. So let's figure out or actually just demonstrate this with a little bit of a proof. When you want to do a proof, just like with your trig identities, start off with the left side, for example, in this case, which is the more complicated side. So the left side, we just copy it. And then what we can do is use the definition of hyperbolic sine and cosine, as you saw on the cover of the video. So there's hyperbolic cosine, and there's the difference and the hyperbolic sine. Notice that these terms are squared. What you want to do now is square the numerator and the denominator of each fraction. So what I did was I wrote the numerator for each twice, because you're just copying the brackets, and squaring the denominator, you get 4 for each. Now, if you apply the distributive property or FOIL for the binomials in the numerator, you end up with several terms here. But the terms that I've highlighted in blue are of particular interest because those quantities will equal 1. Notice that when you add the exponents, you get a 0, giving us e to the 0 or 1. Okay, let's just write this as separate fractions. I mean, you could write this as a single fraction, but at this point, I like to just break things into pieces. So there's those blue quantities disappearing as 1. And here are a bunch of separate fractions. What I've done is I've kind of grayed out the ones that are going to cancel. So the ones that are still bright yellow are the ones that are surviving terms, and the ones that are kind of grayed out are the terms that will cancel out. So eventually you get 2 quarters and 2 quarters. I could write those as half and a half, but I just want you to see how they just match on the previous line. So 2 quarters plus 2 quarters is a whole, which is your right side. And that completes the proof of this hyperbolic trigonometric identity. So hopefully you like that little bonus proof at the end. And hopefully you had some good practice with these derivatives. Generally speaking, they look scary, but they are actually not that bad to do as long as you're comfortable with the chain rule. All right, let's move on.